Hello students, good morning to all. Here I can see we have few participants joined yet, so we'll wait for a few minutes more and then we begin our session. Kindly inform your friends to join the session quickly. Then we'll start our session. Okay, so now without wasting much more time, let's begin the session here. So we'll start the session with the quick revision what we have discussed in our last session. In our last session, we have discussed the solution of the governing differential equation for the damped free vibration, right? So we know that what is the effect of damping and how we are going to introduce the damping, and then we are going to find out the response of the damped system. It means what should be the amplitude with respect to the time. Okay, so here there are three cases that we have discussed earlier in the last session based on the zeta value. The zeta could be greater than 1, zeta could be less than 1 and equal to 1. According to that, our damped system has been divided into the three different cases. Okay, so this is what the zeta greater than 1 is. Greater than 1 is a over damped system, less than 1 is under damped system, and equal to 1 is a critical damped system. What do you mean by zeta? The zeta is nothing but the damping ratio. It is the ratio of the damping coefficient to the critical damping coefficient, right? And these are the simplification that we have discussed in our last session. And we discussed the first case over damped system, and also we find the solution of this over damped system case. Okay, so this is the solution of over damped system, right? So whenever we think about the solution, it means it is gives you the response. Okay, response means the amplitude value with respect to the given time. Okay, what should be the time? So if we consider at zero time, it means that here, if you are at here at zero time, right? This is the time t is equal to 0. Your amplitude value is x0. It is nothing but your initial condition. If you are at 0.1, this could be your x value. If it is 0.2, this will be the x value. So here, this value of x is depends on certain parameter like zeta x0 and its natural frequency. So for a particular system, the natural frequency that remain constant for a particular system if you are not alter the spring and mass, but you can vary the damping coefficients. You can vary the damping, that means what amount of resistance you want to introduce in the system. Accordingly your response getting changed. Okay, but overall behavior looks like this. Fine, so this is what we call the over damped system case, right? Now we discuss the second case, that is what critical damping system. This is what your critical damping system case. Okay, so critical damping, it means that zeta is equal to 1, that we have discussed already. Okay, so zeta is equal to 1, it means the two roots that are similar. I'll show you again. Here you can see this is my two roots S1 and S2. If I keep that zeta is equal to 1 square is a 1 itself, 1 minus 1, that is 0. So this term has been 0. If I keep this term zeta is equal to 1, this term is also 0. Okay, and this is what? Minus 1, right? So this is what? Minus 1, it means minus omega n, minus omega n. So both of the roots that are similar and having the same value, minus omega n. So here in this case, S1 and S2 is equal to minus zeta omega n and zeta is equal to 1. So it's only minus omega n, right? So it means in the critical damping system, the roots are similar. Okay, the roots are equal. And if these roots are equal, then such a solution has been given as in this form, right? Remember, as I already told you, that these are the solutions of the differential equation for various cases, right? So the solution is depends on that what type of root has been obtained for the particular equation. Okay, if the roots are identical or similar, then the equation solution should be different. If the roots are real, then it could be different. If the roots are negative, then it could be different. If the roots are negative and different, then the solution could be different. If the roots are imaginary, then the solution could be different. Okay, so that is a part of mathematics, so we are not going in detail about it. You can refer higher order differential equation chapter in any of mathematics book, where you can find this all basic solutions. Okay, so this is the general solution which can use for finding the solution here. So x is equal to a raised to s1t plus bt e raised to s2t. This is the solution of the equation, initial solution. Now further what we can do is, so we keep that common term from that and this becomes the simplified form of solution. Now further we want to find out this constant a and b, and for that we are going to use the same boundary condition. Okay, so what was the boundary condition that we are going to use here? That already we have discussed, right? So you can check previous notes where we already mentioned the boundary conditions. The same boundary conditions we are applying here. Okay, so what are the boundary conditions? Just try to recall the initial conditions, not the boundary. Sorry, it's a misspell. It's actually initial condition. Initial conditions. What was the initial condition? Yes, that's right. Very good. Anybody else? Anybody else? What is the initial conditions? Anybody else? What is the initial condition? Only one response. Only one students know about the initial condition. What about other? Just try to recall. Here it is. You can see this is what the initial condition. At time t0, x is equal to x0. Right. T0, x dot is also equal to 0. So this is what the initial condition at time t0. We call that x displacement is at maximum value x0. And this is what we call first condition. Second condition, time t0, at the time this velocity must be 0. Okay, this is what your initial condition. So we are using this initial condition in the particular equation and we are going to find out the solution. Okay, so here what we need to do is we are first going to put that first initial condition and then we are going to use the second initial condition. So as you can see, in second initial condition we required the x dot, that is what display velocity. So first we are going to differentiate this term. Okay, so here differentiate the above equation, right? So differentiate this, we get the x dot. So this x dot is equal to now A plus bt. So what would be the differentiation here? A plus bt. So this is a plus sign here. So this could be, we can say it's a, in this case, what we can do is we are using the differentiation by part. Okay, because this two term, let us say this two term is having the t. Okay, this is also, this equation is also having a t. So this part of the equation also contain the variable t, and this part of the equation also contain the variable t, right? So both of this part is contain the variable t. So we are going to differentiate it by part. Okay. So let us keep this part on this part. Any one of this part is kept constant. So first we keep this part as a constant and differentiate this one. Okay. A plus bt. Differentiate the a plus bt. What should be the differentiation here? So we'll keep this part as it is, e to the power of minus omega n into t, this part as it is, into differentiate this term, a plus bt. What would be the differentiation of a? It is a constant, so 0 plus b into t. Differentiation of this term is b itself, so 0 plus b. This is the differentiation of this part. Now plus, right? Now we'll keep this part constant. So a plus bt is constant and differentiating this term. Okay, what would be the differentiation of this? What we are getting? This minus omega n is coming in front of that, and e raised to minus omega n, this term as it is. So this is what the differentiation. Let us simplify this. We are getting here b e to the power of minus omega n t, and this plus minus sign becomes minus here, minus a plus bt omega n e to the power of minus omega n into t. So this is what the basic x dot value, right? So this is your x, this is your x dot. Now we are going to use this initial condition into these two equation, x equation and x dot equation, one by one. Okay, so let's put first the first initial condition into the equation of x. Time t0, x is equal to x0. So put that here. So what we are getting, x, directly we can write x0 is equal to, here we can write as a put the initial condition into above equation of x and x dot, so that we can identify that we are going to put the initial condition into displacement and velocity equation. So this is the displacement equation. So x has been replaced with x0. Now we are going to put the time t is equal to 0. So if you put the t is equal to 0, this term 0 into e to the power of something, like this is 0. So e to the power of 0 is nothing but 1. So what we are getting here, that x0 is equal to directly a. Right? X0 is equal to directly a. Got it? Or let us, I'm just doing with the correct step. Let's say x0 is equal to, let's put that a as it is, plus b into 0 e to the power of minus omega n into 0. So this term is 0 now. E to the power of 0 is again 0. And b into 0 is also 0. So from this we get, this is nothing but your a only. So x0 initial displacement is your constant a, right? Now, what about second initial condition? So once you put the second initial condition, it means x dot is 0 and time t is also 0. So put that into this equation. So x dot is 0, so let's put 0 here. E to the power of minus omega n into 0 into, let's say b here, minus a plus b into 0 omega n into e to the power of minus omega n into 0. Right. So here this term becomes 1. This has been 0 because multiplication has been 0, and this term is becomes 1. So what we are getting after the simplification, we are getting here 0 is equal to b, this term is 1, minus a omega n. So this is the equation here, b minus a omega n is equal to 0, right? So from this, what we can write, the constant b is equal to a omega n, right? And what is the a now? This a is equal to x0, right? So here we can write this b is equal to x omega n, right? So these are my two constant value. A is equal to x0 and b is equal to, so here we can write a is equal to x0 and b is equal to x omega n. So these are my two constants, a and b, right? Now what we need to do next, we just put this constant a and b value into the initial equation, this equation which contain the displacement function. So let us put this put the above constant value, above constants into displacement function x, let's say into the displacement function x. So what we can get now, x is equal to a plus bt to the power of something. So we are going to put it into this equation. So x is equal to a is equal to x0 plus b into t, that is again x0 omega n into t into e to the power of minus omega n into t, right? So here you can see we can keep that x0 common. So x0 into 1 plus omega n into t e to the power of minus omega n into t. This is your final solution of the equation if it is critical damped system. If it is critical damped system, right? And if you get the response curve, the response curves could be look like this. Let's consider this is the time variable, this is the displacement variable in this direction, and if you draw the response, then the response could be looks like this. Initially, if you consider the time t is equal to 0, if you keep the t is equal to 0, this is 0, this is 0, so it's having initial displacement x, so it is at here somewhere. And if you get, and if you increase the time, you will get higher the value of x0, higher the value of x0, and then it will be going like this, right? So this is the response in case of the critical dam system, right? So this is called the critical dam system, clear? And this is the equation of the critical dam system. So first kindly note down this thing in your notebook and then we'll proceed further, okay? So note down this thing in your notebook quickly and then we'll go for a next step. Yes, it is also a non-vibratory system, non-vibratory motion, because the system is aperiodic. Okay, so this is also considered as a non-vibratory system. Okay, done everyone? Is this part is over now? Okay, fine. So now, what is the conclusion here? The conclusion of this is what? So look at this equation first. This is the response equation, which is actually in terms of initial displacement and natural frequency. So once you disturb the system initially, then the behavior of the system could not be directly depends on this displacement, because it is initial value. You just displaced the system by some amount and let them vibrate, right? So this being considered to be as a constant value, omega n, that is also your natural frequency. So you cannot change the natural frequency until you change the mass and stiffness, right? So that is also constant for a particular system. So that value is only dependency on the time. Okay, so if you change the time, you will get another value of your natural frequency, sorry, displacement, right? So at a particular time, you have this kind of response, right? And according to this, as per looking this response, you can say that the system will have the motion only one side of the mean position. It is not going another side of the mean position. So this system is also having a periodic motion. We call this is as a non-vibratory system, just like as the overdamp system. This is also non-vibratory system, because if it is only vibratory, once it cross the mean line, it means to and fro motion about the mean position, it is the vibratory system. Otherwise, we consider it as a non-vibratory system. Right now, generally, this type of you can see, you can observe this curve as compared to the previous. Here, once you start vibrating of this type of damping, it is quickly come to the equilibrium position, near to the equilibrium position, and then it becomes stable, stationary. Okay, and it's take a longer time to be in exact equilibrium position, right? So it quickly come back, and then it's a little bit take more time. So it is just like as the hydraulic door opening and closing. Just you just see in our classroom doors, there are having hydraulic system, right? Once you open, it quickly come to the equilibrium, near to the equilibrium, and then it takes some time to exit closed, right? So this kind of hydraulic systems will have this type of critical dam system in behavior is just like this, right? So this is what we call the critical dam system. Okay, now let's move to the next part, is the under dam system. Fine. Is there any query in this critical dam system? You can ask. Otherwise, we'll proceed for the next case number 3, under dam system. Is it fine? Is it okay, everyone? About this critical dam system? And then we move for the next phase. Okay. It's here concluding remarks that I have not mentioned. You just write the concluding remarks in your words. Okay. As I said. Okay, now let's move to the third case. Nothing but the under dammed system. Is having the zeta less than 1. Okay. If the system is having the zeta less than 1, that is nothing but your under damped system. Right. So just again recall the two roots. I'll just show you the two roots again. You can see these are the two roots that we initially consider. Okay. And if we just assume if that value is less than 1, what happened? If you consider the value of zeta is less than 1, what happened? Let's say less than 1 means 0.5, 0.6, 0.8. If you square of that value, 0.6 square, 0.3 square, so 0.6 square is 0.36, 0.8 square is 0.64, right? So it is always being less than 1, right? So if you subtract the value of 1 from that less than 1, it's having a negative value. Okay, just a minute. Okay, sorry for the disturbance. So what we are discussing here, we are discussing if you consider that zeta value less than 1, then the square value is always being less than 1. And if you subtract minus 1 from that value, which is actually less than 1, it is nothing but negative value. So we cannot find the negative value, let's say under root of minus 1, under root of minus 2, under root of minus 0.5, whatever. So under root value or under root of any negative value is not possible. So what we can do for this kind of case, right? So for that, we need to use some imaginary value. Okay, so here, what we can write, if you consider the zeta less than 1, we are finding the roots having some imaginary values. Okay, so here we use I, which is your imaginary value, which is nothing but under root of minus 1. I hope you understand this kind of mathematic terms that we can use if you have some system having any imaginary parameter, right? So this is what imaginary value I, right? It's an imaginary unit. It is nothing but your imaginary unit. Okay, this is your imaginary unit that we can use here. So now your roots, the roots is becomes minus zeta plus under root of zeta square minus 1, that has been changed to 1 minus zeta square, and here I multiply I, right? So previously it was zeta square minus 1, but that zeta square minus 1 is negative, so we just replace 1 minus zeta square and we'll keep that I constant. If you put it under root of I, we'll get the same value. Okay, so this is what the new position of your roots. Similarly, S2, it's just like minus zeta minus I under root of 1 minus zeta square into omega n. Right? So these are my two roots. Why we have changed the roots? Because of the zeta value less than 1, and if you put that zeta value less than 1, we are getting the root somewhat imaginary, and this is how we can get the imaginary roots and how we can deal with imaginary roots by introducing the imaginary unit I, right? This is the two roots now. Now what we have to do is we have to use these two roots in the condition, in the value. Here again you can see if the zeta is any other value, it's a negative and distinct. Okay, the negative value and it's a distinct value. It means it's a different roots. It's not in same roots, but it is having some imaginary values, right? So what should be the solution of this? It is quite similar to the overdamped system, that initial assumption is x is equal to a e to the power of minus zeta plus I under root of 1 minus zeta square into omega n into t plus b e to the power of minus zeta minus I under root of 1 minus zeta square into omega n into t. Right. Now further we just simplified it again. What we can do now? You can see we can split this cell. This is nothing but e raised to minus zeta as a one term plus e to the power of this term is being the another term, right? So we just split the cell, and what we are getting here, we are getting like a e to the power of minus zeta omega, sorry, minus zeta omega n t into e to the power of I under root of 1 minus zeta square into omega nt, right? So we can split this in this form, plus b e raised to minus zeta omega nt into e to the power of minus I under root of 1 minus zeta square into omega nt. Right? We just split in this form. Further, you just see that this two term is common. I mean both of this, both of the component of the equation. So we keep that term constant, minus zeta omega nt here, and a e to the power of I under root of 1 minus zeta square omega n t plus b e to the power of minus I under root of 1 minus zeta square omega n to t. Right. So this is the simplification of the displacement function. Now here, as per the Euler's theorem, we can simplify this based on the Euler's theorem, and we can write this equation as in the form of x e to the power of minus zeta omega n t sine of, or further, before using this, let us further simplify it, you will get a more idea. So here what we can do for further simplification, e raised to minus zeta omega n t into a e to the power of, now we just keep this term, I'm talking about this term from here to here. Let us consider one another constant value which called a damped natural frequency omega d. Okay, so we replace this term with omega d. So I as it is, this term has been replaced with omega d into t, right? This is also natural frequency, this is also natural frequency, but here in suffix d it indicates it's a damped natural frequency, right? So this two value is quite different, because in a damping there is effect of damping is there, so the damped natural frequency has been less than the real natural frequency of the system, so we can replace this term as a damped natural frequency, right? Same way, another component e raised to minus I omega d into t, right? Where the omega d, okay, what we can write, where omega d is equal to under root of 1 minus zeta square into omega n, right? So this is the equation that frequently we are going to use to find the damped natural frequency. Okay, this is your damped natural frequency. Okay, remember, this is also natural frequency, this is also natural frequency. If it is written here in suffix d, it indicates damped natural frequency, right? It's called here damped natural frequency. Okay, got it? So this is your damped natural frequency, and then finally we can write the solution as in this form, as per the Euler's theorem, that x is equal to capital X e to the power of minus zeta omega n t. This term kept as it is. Now only we deal with this. So this can be right as the sine omega dt plus phi. Okay, again it's a mathematical term, right? So we can replace this term x a e raised to I x plus b e raised to minus ix, that we can write like sine of x plus phi. Okay, sine of x plus phi. This is what the mathematical term. So we can write the solution of this equation in this form, right? So this being the solution of this equation, right? So here x is the initial displacement, and if you put that omega n and t, if you use these initial conditions and boundary conditions, we are getting this solution, right? So here I'm just writing it directly after putting these all conditions, and we'll get the solution is in this form. Fine. Now what we are getting here as a part of the solution, and if you want to plot this diagram, how it's look like that and how we'll get it. Okay. So the response of the system, if you draw the response, it just like this. This is what the time in the direction. This is the direction of x, right? So what should be the response? The response is like this. Right. So this is what the response of the system here. And here you can see the system will have a periodic motion, right? Because if you consider some value of sine, so sinusoidal functions are always having this kind of responses, right? So this is what we call the response here. So here, this is nothing but your initial displacement. Let us say this is your x value, or we can say x1. This is what we call x2. This is what we call x3, and so on, right? Just try to recall our damped vibration system we have discussed. Okay, we have discussed in our lab session damped torsional vibration, in which we are getting some response of the system, and you can see that response is very similar to this one, where we are getting the different amplitude value at different time period. Okay, so this is what we call the different amplitudes value, right? And here this distance, what is it called? Anybody? What is this distance called from here to here? Okay, pitch is the answer is related to threadings. Okay, in vibratory terms, we don't have pitch, right? Yes, it is called time period. Okay, what is it called? Time period, right? So this is called time period. What is the time period now? As you already discussed that damped vibratory system. Okay, so generally our time period, what how we can write that 2 pi by omega time period for the damped vibration. That's why we are writing omega d. That is what your damped vibration. And here you can get this value as a 2 pi divided by under root of 1 minus zeta square into omega n. This is your time period for the damped vibration, right? So here, in case of the underdamped system, we come up with the two parameter here. One is the damped natural frequency and damped time period, right? And this is your real vibratory system. So whenever we discuss or whenever we introduce that any damping system, any damper into any of vibratory motion, which is actually used to retard the motion, there are always this kind of underdamped system in which the zeta is less than 1, right? So we always prefer the underdamped system, which is going to use as a damper in case of vibratory system, right? Because in previous two, overdam system and critical dam system itself is a not a vibratory system, right? It just a periodic motion. Got it? So all or most of the mechanical system, dammed mechanical systems are nothing but the underdamped systems. Okay. So this is all the three cases that we have discussed: critical dam system, underdam system, and overdam system. Right? So kindly complete this write-up. So kindly note down these things in your notebook quickly. Okay, so now just complete this part. Okay, so with this, we are ending the today's session where we discuss these three cases of damped vibration. We'll continue with the next topic where we are going to discuss the logarithmic decrement. Okay, so this is all about today's session. Now we'll continue the part in our next session. So now you just write your name and number in the chat box for attendance purpose. And after the writing, you may leave the session and join the next session. So till have a good day. We'll see you in the next class. Here I can see some students are still in the meeting. Kindly write your numbers and leave the session as I'm going to end it. I'm going to end the session.